The FFGX Constellation class program was launched with a deceptively simple premise: to modify a proven European FREMM frigate design to meet U.S. Navy standards while maintaining 85% component commonality as a low-risk solution to the Navy's frigate gap. Instead, the program has become a textbook case of systemic procurement failure because aggressive Americanization and continuous requirements creep reduced commonality to a staggering 15%. The hull was lengthened by 24 feet and widened by 4 feet to accommodate heavier armor, domestic power systems, and the EASR radar suite, which triggered a cascade of redesigns, including the consolidation of electrical panels that forced a complete overhaul of the engine room and weight distribution. The result is an unplanned weight growth exceeding 750 metric tons, which is a 13% increase from the original baseline that has compromised stability margins and eliminated growth margins for future upgrades, leaving the Constellation as a heavier and slower vessel born without the room to adapt to emerging threats. The physical consequences of these design modifications are devastating to operational capability because the lengthened and widened hull intended to restore stability only added more mass, causing the top speed to reportedly drop below 26 knots. This is well below the 30+ knots required to escort a carrier strike group, meaning a frigate that cannot keep pace with the carriers it is meant to protect has effectively lost its primary mission. The Navy attempted to pack mini destroyer capability into a frigate hull, resulting in a vessel too slow for high-end escort duties and too expensive for low-end patrol missions, essentially compromising the platform before its first deployment. With Constellation delayed by at least 36 months, attention has shifted to the Legend-class national security cutter and its militarized variant, the PF-4921, as a proven 4,600-ton hull that is faster than the current frigate design. However, the technical transition involves severe risks because the NSC's current diesel generators are insufficient for the peak electrical loads and heat rejection requirements of Aegis and EASR, necessitating a complete overhaul of the electrical architecture. Furthermore, upgrading the NSC from Level 1 to Level 2 survivability to survive missile hits requires adding Kevlar armor and redundant systems, which triggers a new weight growth spiral that the hull was not originally designed to absorb without significant structural reinforcement. The primary technical bottleneck for any frigate-sized platform is the capacity to generate and dissipate electrical power, because modern AESA radars, like EASR, are incredibly energy-intensive. The NSC's current power generation is designed for Coast Guard patrol and cannot support the several megawatts required by high-end combat systems without a total overhaul of the HVAC and electrical systems. While the Navy could choose a simplified combat system with a smaller radar to fit the existing power budget, this would force a degradation of the anti-air warfare capability that was the original justification for the program. The U.S. Navy faces an existential dilemma in the Indo-Pacific regarding whether to build a few high-end ships or a massive fleet of low-end hulls to meet the pacing threat. While high-end ships are needed to survive hypersonic missiles and drone swarms, the distributed maritime operations concept requires a high number of hulls to complicate adversary targeting and cover more ocean. The Constellation crisis reflects an inability to choose between these two futures, leaving the Navy in a state of deep uncertainty regarding its long-term force structure. Adopting designs from Japan or South Korea is often presented as a shortcut, but these platforms carry their own integration risks. The Japanese Mogami class is built to commercial survivability standards that are inadequate for frontline U.S. operations, while the South Korean Chungnam class is tightly integrated with proprietary systems. Replacing these with U.S. Aegis and VLS hardware would require the same expensive Americanization process that ruined the original FREMM-based design, proving that foreign designs are not a magic solution, but merely a different starting point for modification risks. While Asian shipyards are faster and cheaper, outsourcing construction is practically impossible due to the Jones Act and the Buy American Act, which mandate that warships be built in domestic yards to preserve the industrial base. The risk of technology leakage regarding sensitive radar and propulsion systems remains a red line that prevents full overseas production. A joint venture model where U.S. yards build modified allied designs is a more plausible path, though cultural differences in design and quality control often introduce unforeseen delays. To resolve this crisis, the U.S. Navy must adopt a disciplined two-tiered fleet strategy that separates high-end carrier defense from mass-produced workhorse missions. Tier 1 assets like Arleigh Burke destroyers would handle ballistic missile intercept, while Tier 2 would consist of a simplified modular frigate focused on mass production with ESSM and naval strike missiles. The priority must shift from maximum capability to minimum viable lethality that can be produced at scale to ensure the domestic industrial base can sustain the fleet. The most effective what-if scenario involves the Navy performing a radical design freeze where they sacrifice the heavy EASR radar suite for a lighter system like the TRS-4D to immediately restore the ship's stability and speed to 29 knots. If the Navy continues to struggle with the Constellation hull, they should consider a hybrid what-if, where the NSC is built with only 16 VLS cells and focus strictly on anti-submarine warfare to rapidly increase hull numbers in the Pacific. Another critical what-if explores a policy exception to the Jones Act that would allow U.S. shipyards to outsource only the basic hull and machinery construction to Japan or Korea, while keeping the sensitive combat system integration in domestic yards to cut construction time by 40%. Ultimately, the Navy must accept that a good enough fleet delivered today is superior to a perfect fleet that arrives too late, requiring a shift in focus from technological optimization to industrial velocity to maintain dominance in the Pacific.